Well, I thank you to the organizers for organizing this wonderful meeting. I haven't thought about this topic in a little while, and so this is kind of an overview of generic Muchnik reducibility. Let me first tell you what that is. So first of all, Muchnik reducibility between structures. If I have countable structures A and B, then A is Muchnik reducible to B if every omega copy of B, that is a presentation of B with universe omega and whatever functions and relations coded on over that universe, every omega copy of B computes an omega copy of A. Given an omega copy of B as an oracle, you can compute an omega copy of A. Now this is a special case of Muchnik reducibility. It might be more precise to say that the problem of presenting the structure A is Muchnik reducible to the problem of presenting B, but we won't say that because it's a little bit long, and this is the only case of Muchnik reducibility we will discuss today. The W in the reducibility is for weak, and it's to distinguish Muchnik reducibility, which is non-uniform, from the uniform Medvedev reducibility. But again, we won't talk about that. Now, the point of the talk today is that Muchnik reducibility does not apply to uncountable structures, and there are ways to extend computable structure theory beyond the countable, and I think we've seen some of that. In particular, computability on admissible ordinals, alpha recursion theory. There's also computable analysis and extensions which give you computability on separable structures. We're not going to talk about that. We're going to talk about an idea of Noah Schweber, I guess in this room, Schweber, who extended Muchnik reducibility to arbitrary structures in a very naive way. You have two arbitrary structures, just take a forcing extension that makes them countable, and then ask if there's Muchnik reducibility between those countable structures. Now what makes this work is that it doesn't matter what forcing extension you took to collapse it. Schoenfeld absoluteness tells, a simple Schoenfeld absoluteness argument tells us that A is generic Muchnik reducible to B if A is Muchnik reducible to B in every forcing extension that makes them, or every/any forcing extension that makes them both countable. So the combinatorics of forcing are really not going to play a role here. I guess I should apologize for that, but there will be some descriptive set theory before the end. And so this really does extend Muchnik reducibility on countable structures. Okay. Now, are there any questions, by the way, because I know it's a diverse audience. I want to make sure that hopefully people understood the first couple of slides. Well, the goal mainly of this talk and of this sort of initial burst of work on this subject was to understand the Muchnik degrees of, well, Cantor space, Baire space, the field of real numbers, and related structures, expansions, and to some extent extensions of those. And that makes sense. I mean, the first uncountable structures you think of, okay, a lot of you, it's probably ordinals. But the second example would be, these nice versions of the continuum. Now, consider a forcing extension that collapses the continuum. And let I be the ground model's copy of 2 to the omega or power set of omega, the sets in the ground model. By absoluteness, it's closed under Turing reduction, join, the Turing jump. Well, I say much more. I mean, definitely more than that. It's a very nice countable ideal in the forcing extension. It's at least a countable jump ideal, and we'll use more than that before we're done. Just notationally, we'll say that a function is in I. I mean, I is a collection of sets from the ground model. We'll say a function is in I if it's computable from an element of I. Same for a real number or a tree or whatever. Okay. So An enumeration of a countable family of sets is a sequence of sets xn. So the point is that the family is equal to the sequence of xn's. The order of the sequence doesn't really matter. It's just a way of listing all the sets in S. An enumeration and an enumeration is injective if each set appears exactly once. Now, for any countable ideal, every enumeration can use an injective enumeration, so we're not really going to have to worry about that distinction between having an enumeration and having an injective enumeration. This is a simple finite injury argument. Basically, things look the same. You throw one of them away and maybe try again later. We can define an enumeration, we can also define an enumeration of a countable family of functions in the same way, and the same lemma holds that if we have an enumeration, we can, with a little finite injury argument, thin it out to an injective enumeration. Okay, so let's start with Cantor space. Cantor space is the structure with universe to the omega and predicates telling us, predicates Pn, telling us if n is an x. So, Knight, Montalban, and Schweber, in the first paper that mentioned generic Muchnik reducibility, observed that Cantor space is generic Muchnik reducible to the field of reals. You really don't even, you need much less than the field of reals. But let's just go through this example slowly before we sort of rocket ahead. So taking a forcing extension that collapses the continuum, and let I be the ground model's version of 2 to the omega, Ri, the ground model's version of R, and Ci, the ground model's version of Cantor space. So Ri is the real numbers in I, Ci is the restriction of, well, this structure to just the sets in I. And I said that bit already, and that's why pauses are kind of silly. Okay. So this, but just to be clear, this is the ground model's version of 2 to the omega, and there's, it's easy to see what the ground model's version of Cantor space and the real numbers should look like. Now, from a copy of just Ri with plus and less than, we can compute an injective enumeration of I, right? Non-uniformly say I know 0 and 1, and then I can start figuring out, well, what's 1/2, 1/4, 3/4, and using comparison, I can then, given a real number, I can then start writing out its binary expansion. A real number between 0 and 1, I can write out its binary expansion. If I'll notice if it's a dyadic rational, because I'll actually see that it's equal to one of the dyadic rationals that I'm enumerating, and then I can give both of its expansions in my list. And in degree D, this is also easy to see, computes a copy of Cantor space over the ground reals, if and only if it computes an injective enumeration of those sets. This is almost, there's nothing to this. This is, well, except the fact that injective is free. So therefore, given the reals with plus and less than, we get Cantor space, and of course, it's not hard to get the reals with plus and less than from the reals with plus and times. And this is all the ground model versions. And so it tells us that Cantor space is generic Muchnik reducible to, say, the field of reals, and the reals with plus and less than are in between. And they asked, does the reverse hold? And it seems like it shouldn't. This is a much more complex, interesting structure than just that guy. I'm not, this is the first of the 4 questions, and I don't have time to, So this was answered twice independently. I'm gonna tell you the answer that I was involved with, but I'm also the one speaking, so that's it. What do you expect? Anyway, I'm not going to keep anyone in suspense for any of these 4 questions. As soon as I ask them, I'm gonna tell you the answer because we just don't have time for suspense. So no, the reals are not generic Muchnik below Cantor space. And Donnie Greenberg and I showed this by considering Baire space, and Baire space is very similar to Cantor space in how we present it. We have the universe is omega to the omega, and we have predicates for every string sigma, saying that sigma is a prefix of F. And a degree D commutes a copy of Baire space if and only if it commutes an injective enumeration of the functions in I, which, by the way, is not hard to see. That's equivalent to giving an injective enumeration of the infinite sets in I. That's pretty straightforward. And I described how you would enumerate from the reals with plus and less than, how you would enumerate the sets. But in fact, the case where you find out that you're looking at a dyadic rational, don't give both representations now, just the one with infinitely many ones. And now you've given me an enumeration of the infinite sets and therefore of the functions. So it's very much the same thing. So what we did was we proved that for any countable Scott ideal I, now this is just computability theory, forcing in computability theory, but just a fairly simple computability theory argument that there's for any such I, countable Scott ideal, the Scott ideal, weaker than a jump ideal, an omega model of weak Kernig's lemma. Reverse mathematics is in the title of this conference, so I don't feel bad giving that description. I wouldn't normally give that description. So there's an enumeration of I that does not compute a function that dominates every function in I. So there's an enumeration of I, just a listing of the sets in I that doesn't compute a dominating function. And of course, if you compute an enumeration of the functions, then you could easily build a dominating function out of that. So it can't compute an enumeration of the functions in I. There's so much I want to say about this, but like the fact that Karl Jockisch basically gave the converse of this in the 72. He proved that a high degree every high degree, I can say this a little bit better. A degree is high, its jump computes zero double jump, if and only if the degree computes a list of all the computable sets, if and only if it computes a list of all the computable functions. So for computable, listing the functions and the sets is the same. And for any non-Scott ideal, listing the sets and the functions is the same. But once your ideal has a little bit of closure, then they're different. Okay. So anyway, this implies that Baire space over I is not Muchnik reducible to Cantor space over I, so Baire space is not generic Muchnik reducible to Cantor space. Okay. And, well, we already know that Baire space is below the real field, so the real field is not below Cantor space. We got a separation without having to think about the reals at all. We didn't stop there, though, because I think what's interesting about this is that what makes, in terms of generic Muchnik reducibility, what makes the field of reals complicated has nothing to do, or very little to do, with the field structure. And in a couple of papers, some of this is proved by one group, some by the other group. I mixed it all together, but we showed that Baire space is equivalent to the field of reals, generic Muchnik equivalent, and actually Auguste, Knight, and Schweber are the ones who showed that you can keep going. You can add the exponential function, the sine function, any O-minimal function. Both papers used tameness. We used quantifier elimination. They used O-minimality, as you know, unsurprisingly from the statement of the theorem, to recover from injury. So you're trying to build this structure, and every now and then you make a mistake, but you use the fact that you have this tameness to recover from that injury and keep building the structure. Baire space is not below Cantor space. And that's because there's a listing of the sets in a Scott ideal that does not compute a dominating function, a function that dominates all functions in the Scott ideal. Okay. Here, just to point out, this is not an O-minimal extension, but it's a generic Muchnik equivalent to an O-minimal extension, so it's not different than the other examples. So they asked, is that tameness necessary? Or is there some bad continuous function that gives you an extension of the rails that's strictly higher? And this is our second question. And like I said, I'm not going to leave you in suspense. The answer is no. In fact, every continuous extension of the reals is going to be equivalent to the field of reals. That tameness was not necessary. That it just happened that both papers kind of didn't get the right method and used a little bit more than we needed. Okay. So when when building a structure over the ground model reals, it would be very helpful to have access to the jump. I mean, that's like one of the stupider things I put on the slides. Obviously, it would always be nice to have the jump. And our main lemma actually gives us access to the jump in a specific way. So if I have an enumeration of sets xn, the corresponding running jump is the sequence of all jumps of joins of finitely many elements. I mean, okay, it's written here as like the jump of the join of the first n elements, that sequence, but really it just gives you the power to compute the jump of the join of any finite number of elements. And even if we know that I has those jumps in it, we're not, just to be very, very clear, we're not able to point to the element of I that is the jump. We can just also compute the jump along with the listing of the sets. And that's an important distinction. So computing the running jump is equivalent to, pauses are stupid. Uniformly being able to compute the jump of the join of members of the enumeration. Finitely many. Okay. So, we showed that if I is a countable jump ideal, every enumeration of the functions in I computes an enumeration of the sets in I along with the running jump. And the proof is a delicate finite injury construction, and I'm going to say a little bit about it on the next slide. So, here's a restatement of it. To compute the next set in the running jump, we guess a function in I that majorizes the corresponding settling time function. The settling time function tells you, for things that are actually going to enter the jump, how long you have to wait to see that. And there's a minimal monotone function that does that. If we're wrong, in other words, we guessed a settling time function a function that was too small, say. So we thought, oh, this doesn't go into the jump. We were wrong. Well, there's an injury and a new guess. But how do we recover from injury? We use a low basis theorem to patch up what we have so far. And I really like this proof because it uses the low basis theorem as a module. And at any given point in the construction, you have more and more and more. Well, as the construction goes along, you have more and more and more copies of the low basis theorem, basically, like the low basis theorem modules running to produce, these patches. And this is what makes it, despite the fact that it's only finite injury, this is what makes it a little bit delicate. Anyhow, we need to start with an enumeration of the functions because we need to be able to search for these settling time functions. It's one of the functions in the list. We just we guess maybe it's this one, no, maybe this one, no, maybe this one. Eventually we'll be right. And we can only hope to produce an enumeration of the sets in I because you can't use the low basis theorem in Baire space. It's a Cantor space theorem. So we really are getting exactly what we can get. And you can prove that any sort of stronger looking variation of this is just false. Okay. So now that we have this running jump, it's quite easy to build these expansions of the reals by, say, any countably many continuous functions of any arities. So we take these parameters that have to be in the ground model, coding our continuous functions, coding them in the sense that you can, in a sigma 1 way, recognize you got the answer wrong. And then we take the enumeration of the sets in I in the ground model along with the running jump, And then we just start doing things like using the jump. Okay, well, this just tells us how do I represent a real number. I represent it in terms of a binary expansion and a natural number. But using the jump of x0 join x1, I can check to see if z0 x0 is equal to z1 x1. That's easy enough. And because I have this code for the continuous functions, using the jump of the code joined with all the binary expansions I need, I can check whether fi on, say, these inputs is equal to that output. Like I said, the code lets me see that I'm wrong in a sigma 1 way, so the jump lets me know if this is right or wrong. This is all very simple. Like, there's nothing going on in this proof. You can also check plus and times, and therefore you just build a copy of the field with all these continuous functions. Everything's easy because we have the jump, which is a really nice thing to have. There's no injury because all that injury happened when we were building the jump. This moved all the hard stuff away from having to think about the real numbers and into this nice computability theoretic lemma. And we didn't have to think about game topologies at all, as it turned out. Okay, now the running jump can also be used to build continuous expansions of Cantor space in the same way. So any expansion of C by countably many continuous functions is also, well, generic Muchnik below Baire space. The natural expansions of C turn out to be, it's not very hard to see that expansions of Cantor space don't have to be at the level of Cantor space. There's very simple ones that aren't, like if I add the shift to Cantor space or the join. And that's because if I add the shift or the join, I have a way to recognize that a set's CE. A CE way to recognize that a set's finite. In other words, given the shift and a set I with only finitely many ones, well, I just shift it, keep comparing to the all-zero sequence. Eventually, it is the all-zero sequence. And I go, haha, I don't want to list this one when I'm trying to list the functions, when I'm trying to list the infinite sets. So that's what you do, and you can show that expanding by the shift or similarly the join gives you Baire space back because you can just list the infinite sets. Okay. On the other hand, continuous, and this is really equivalent to closed, well, with a little bit of work. Continuous expansions of Baire space can be more complex than Baire space. And here's a very silly example. Let's look at the set Z, which is F join G join H, where H is a settling time function showing that G is F jump. This is a closed subset of Baire space. In fact, it's a effectively closed set. It's a pi 0, 1 class. You'll see if you're wrong. Anytime you're wrong, you'll just see in a sigma 1 way that you're wrong. And if I really wanted to not think about closed sets but continuous functions, I could do something very silly. I could take the continuous function that has Z as a 0 set. But let's not do that. Okay, and given a countable jump ideal, any copy of Baire space over that ideal with join and this closed set, which is continuous, obviously, and this closed set Z, computes an enumeration of the functions in the ideal along with join and jump as functions on indices of the enumeration. This is what I was saying the running jump did not give us. Now, I can say, I have this function f in my enumeration. Where in my enumeration do I have to look for the jump? Oh, there it is. Okay, there's almost nothing to say. You just do a search, and you find the functions that you're searching for, and you check. Okay, but basically, Cantor space with join and jump, Baire space with join and jump, they're both generic Muchnik below Baire space, this continuous / closed expansion of Baire space. So now I'm not even trying to answer a question anymore. I answered the second question and it just kept talking about continuous expansions. I want to show that this structure, I want to tell you why this structure is actually strictly above Baire space. Yeah. I want to show that that this Cantor space with join and jump is strictly about Baire space. All right. But we need a little bit more closure in our ideal, and everybody knows that probably everybody knows a better name than Hyperscott ideal. I want an ideal I such that whenever a tree is in the ideal and has an infinite path, then it has an infinite path in I. These are known as, a Hyperscott ideal would be the same as the Cessna beta model. Again, for those of you that do reverse mathematics. But yeah, it has the sort of closure that obviously, if I is the ground model's reals after a forcing extension that collapses the continuum, I has to have. And Y is Schoenfeld absoluteness in its simplest form. It's the pi11 version of Schoenfeld absoluteness, right? That if you have a tree in the ground model with no path, then the ground model has a rank function witnessing that it's well-founded. But of course, that still witnesses that it's well-founded in the extension. And so the ground model reals are Hyperscott ideal. I have asked people, what should I call this? This is a dumb name. The best suggestion I had was Great Scott. But it's too silly. So assume that I is a countable Hyperscott ideal. Then there is an enumeration of the functions in I that does not compute an enumeration of the functions or sets, it's equivalent, in I, along with a join and jump as functions on indices. This is a more fun proof than the first result I stated, but that's not. I don't have time to give it. This is a survey. What it tells us is that these structures are not below Baire space. And in fact, that there's a continuous expansion of Baire space that is strictly above Baire space in the generic Muchnik degrees. Oh, yeah. Now, it turns out that all of these structures are generic Muchnik equivalent, and that's because, in fact, Cantor space with join and jump is above all Borel structures. And I'll just quickly tell you what a Borel structure is. It's exactly what you think it is. You take, say, Baire space, you take a Borel set and a Borel equivalence relation, and that defines your universe. And then you take Borel functions or relations that are compatible with the equivalence relation. Anyway, it's not too hard to show that every Borel structure is below Cantor space with join and jump. So this is what we have. We have Cantor space, Baire space, and what we call the Borel complete degree. Between Cantor space and Baire space, there's maybe a lot of stuff, but it definitely includes all continuous or closed expansions of Cantor space. Between Baire space and the Borel complete degree, we have all Borel expansions of Baire space, and more. Baire space is generic Muchnik equivalent to any continuous or closed expansion of the reals. You saw that. And if you want to think about jumps of structures, these are actually really nice degrees. Each one is the jump of the previous. There's even one below Cantor space that Noah Schweber talked about in his thesis that jumps up to Cantor space. So you have this sort of, you're starting to see like a spine of, well, interesting structures in the generic Muchnik degrees. Is there a generic Muchnik degree strictly between Cantor space and Baire space, however? I said, hey, look, all the continuous closed expansions are in there, but maybe they're all there or there. Actually, that's the case. But there is a generic Muchnik degree strictly between, but it can't be one of these continuous or closed expansions of Cantor space. And so those are the next parts of the talk. And I have a little bit of time, so that's good. Third question. Yes, I've already told you, really bad at suspense. There is a Muchnik degree strictly between Cantor space and Baire space. But this is going to be an unsatisfying example. I don't have a satisfying example. Okay. It's also, I'm afraid, this section might be a little less detailed than other sections. Most of the tools we use were just handed to us, and so I'm just going to describe them. But first of all, it's going to be important to understand the complexity of definable sets both before and after the forcing extension. So this is where we get we sort of vaguely touch on some descriptive set theory. Okay, so we say that a relation R on the structure is computably sigma n, so over the structure M, if it is definable by a computable sigma n L omega 1 omega formula with finitely many parameters from the structure M. It is a well-known theorem in computable structure theory that if M is countable, then a relation is computably sigma n over M if and only if it is relatively intrinsically sigma 0 n. That is, it is sigma 0 n in every omega copy of M. I mean, that's a really nice theorem. It links computability to definability in exactly the way you would want it to for the countable structures. But hey, we're going to make things countable before we think about them. So really, given that satisfaction and computability are both absolute, what this tells us is that a relation is computably sigma n over M if and only if it is relatively intrinsically sigma n in every forcing extension that makes, any forcing extension that makes M countable. You can also measure the complexity of definable sets in terms of the projective hierarchy. So here we have a complexity profile. So for example, it's pretty easy to see that the sigma 2 computably definable sets in Baire space are the sigma 1, 1 sets, but in Cantor space, it's the sigma 0, 2 sets. Or that the sigma 5 or sigma 1, 4 in Baire space, but sigma 1, 3 in Cantor space. This, by the way, oh, these are sharp. This is an if and only if, actually. These are exactly the sets that are definable in this way. Point 2, the loss quantifiers, you know where they went. Because you know that when, say, you write a sigma 1, 1 definition in normal form, well, it looks like a function quantifier followed by a single set quantifier. But if you write it, sorry, number quantifier, function number. If you write it using quantification over sets, you have the function quantifier and then 2 number quantifiers. So you lose 1 here and 2 here. And that's exactly where the loss quantifiers are going. There's also, by the way, and I'm not going to write it out, but this gives us actually extremely easy, the easiest separation I know of between the Muchnik degrees of Cantor space and Baire space, because basically, in a sigma 2 way, you can define a sigma 1 set in Cantor space if you're in Baire space, but in Cantor space you can't, and that separates them. We're gonna look at a different a more complicated separation, but one that's useful for giving us an intermediate degree, and that is we're going to look at a linear order that is going to be generic Muchnik below Baire space, but not Cantor space. And this is where I'm going to start just waving my hands more, because, like I said, all the computability and linear order stuff we needed was just handed to us. This was well known. So we can code why not? We can code a subset of Cantor space into an uncountable linear order using what's called a zeta coding. So using copies of zeta as delimiters, and encode all elements of Cantor space along with markers telling us which ones are an X and which ones are not an X. And this is all stuff I don't want to get into too deeply, but we understand these kinds of codings well enough to know that given such a linear order, well, if X is computably pi3 over Baire space, then Lx will be generic Muchnik reducible to Baire space, and if Lx is generic Muchnik reducible to Cantor space, then it's computably sigma 4 over Cantor space. And if you remember, one of those is going to be equivalent to pi 1, 2, and the other one to sigma 1, 2. If you take X to be pi 1, 2, but not sigma 1, 2, then X will be Lx will be generic Muchnik reducible to Baire space, but not to Cantor space. So, yeah, I'm not going to get too deep into this, but if you know the linear order work, this is just a restatement of it. Linear orders work. I don't know why I keep thinking there's only one linear order. Okay. And now what are we going to do? We have this linear order that is generic Muchnik below Baire space, but not Cantor space. We join it up with Cantor space, and we get something that's strictly in between. And why? Because having that linear order does not give you Baire space back, because basically, it takes a couple jumps to even figure out what's going on with the linear order. The first couple of jumps, linear orders look stupid. Well, linear orders don't really compute anything, and the first jump doesn't compute anything. But after that, we're just trying to, yeah. So basically, using Knight's theorem that the two quantifier equivalence classes of linear orders are always simple. We prove this, and like I said, I'm not going to get into detail. All the work was handed to us, but this gives us an intermediate degree. It is not a very natural one. We took Cantor space and we just put it on a linear order that did some funny coding. It doesn't feel that good. So what I want is what? I want some nice expansion of Cantor space that gives me something between Cantor space and Baire space. And I've already told you that that can't be too nice, but let's see what we can say. Okay, so if that linear order stuff was irritating, we're done with the linear order stuff. And now we're going to get into stuff that's actually pretty straightforward. Is an expansion? I don't know, but it can't be continuous or continuous / closed expansion. Okay. So let's look at some expansion of Cantor space with, whatever. Functions, relations, I don't care, stuff. Okay, we want a criterion that guarantees that this expansion is above Baire space. And I'm going to start with the very dumbest version, and then I'm going to build up to better and better criteria, and then use a tiny little theorem from descriptive set theory. All right. First of all, let F be the set of sequences with only finitely many ones. If that set is computably definable over M, then then you can recognize the ones with infinitely many ones, and you got Baire space. Okay. If it is delta 2, computably delta 2 in M, well then add a little injury. You don't immediately know which sequences you're trying to avoid, but you eventually know which sequences you're trying to avoid. It works out fine. We already used more or less this idea. Well, we didn't use that it was delta 2, but here the sets with only finitely many ones is sigma 1, and we got around that with a little injury. It's the same idea. Aha! Nothing special, actually, about the sequences with only finitely many ones. Any countable dense subset of Cantor space, the complement looks like Baire space. So if you can recognize any countable dense subset of Baire space in a delta 2 way over M, you get Baire space. Ah! But who cares about Cantor space? Just if there's any perfect subset of Cantor space and a countable dense subset of that's delta 2, then we're golden. Oh, how do we have our handle on this perfect set? Well, there's a code in the ground model. A tree. There's a code for a tree in the ground model, and that's good enough. Okay, so we went from really simple to actually still pretty simple. There's just something that looks like Cantor space and something that looks like the rationals inside that, and so we can present the complement. Great. That's just a restatement of it. Now, it's also the case that if M is generic Muchnik below Baire space, then any relation that's delta 2 in M is actually delta 2 in Baire space. And that means it's Borel from our complexity profiles earlier. Okay, so now we're going to bring in a little bit of descriptive set theory that I promised. It's a lemma of Hurwitz. If R is a Borel subset of Cantor space, but not boldface delta 2, then there's a perfect subset, P, of Cantor space such that either P intersect R or P complement intersect R is, sorry, R complement intersect, either R intersect P or R complement intersect P is what I should have said. Anyway, what I've written here I think is also correct. It's countable and dense. Hurwitz says that this exists as long as R is Borel but not delta 0, 2. So, putting it all together, if M is generic Muchnik reducible to Baire space and an expansion of Cantor space, and we have a delta 2 definable relation that's not boldface delta 2, then M is above Baire space. That doesn't seem great, but I'm going to take that. I'm going to take the contrapositive of it. I'm going to use the fact that delta 2 definable over Cantor space is the same as boldface delta 2, and I get what we call the tameness lemma. If M is strictly below Baire space and an expansion of Cantor space, then the delta 2 in M and delta 2 in Cantor space definable sets are the same. Okay, so all of that discussion was just to give me this. Okay. And we did use a tiny little bit of descriptive set theory, which, yeah, okay. This gives us the dichotomy theorem for closed expansions. If M is generic Muchnik reducible to Baire space and an expansion of Cantor space by closed or continuous relations functions, then it's either Cantor space or Baire space in the generic Muchnik degrees. Why? Well, I gave you one half of that. What we do is we take a bad enough relation, in some sense. We take codes for the complete positive sigma 1 M type of any tuple, and we package it up in a relation, and then we ask, and then we note that that relation is in fact delta 2 in M. And it's about as bad as any delta 2 in M relation can be. If it's not delta 2 in Cantor space, then hey, we're above Baire space. Cool. If it is delta 2 in Cantor space, then there's a delicate injury argument that we need to go through. But basically, this tuple gives us all the information we need to recover from injury. And so we can show that, in fact, M is generic Muchnik below Cantor space. So little set theory on the one side, little computability theory on the other side. And that's what I really like about this subject is that there's this kind of duality. That's the dichotomy theorem that I already stated. There's another dichotomy theorem. Half of it was proved by Greenberg, Gusa, Turetsky, and Westrick, who did a fair amount of this, a fair amount of related work. It is that if you, instead of looking at closed or continuous expansions, you look at countable, arbitrary, unary expansions, you can't get an intermediate degree. These aren't actually, I'm pretty sure it's easy to see that you can't combine these two. The injury that you have in the two arguments is just different. They don't really combine. So, but between the two of them, they rule out a lot of really natural and nice and unnatural expansions of Cantor space. There's just a lot of examples ruled out now that can't be strictly between Cantor space and Baire space. But we don't know. I mean, we don't know. Maybe there still is an expansion of Cantor space strictly between Cantor space and Baire space. The non-unary delta 2 case is open. Okay. So, yeah. So are there, that's really the one question. But it's not the question I think will be most interesting for this audience. We really, I think in the end, we got sort of hyper-focused on expansions. And there are a lot of other questions you could ask. You could ask, for example, Again, not the question I want to sell here. But are there incomparable degrees between Cantor space and Baire space? An undergrad who went on to grad school at UCLA, but I'm not sure what happened to him afterwards, they took our linear order proof and showed, well, you can code that set at different levels and get a nice chain, but we don't know about anti-chains. If you assume delta 1,2 wage determinacy, all the stuff I've been saying about between Cantor space and Baire space also holds between Baire space and the Borel complete degree. This is mostly for the Hurwitz theorem at the next level. And we have the same questions. The questions are a little bit worse. We know that things are nice for continuous expansions, but really, Borel should be, Borel is what, should be the analog of closed there, I guess, and we don't know what's going on with, or Borel should be the analog of delta 2. Yeah, Borel is the analog of delta 2, so there's a much bigger gap. Okay, but anyway. But I think what I want to say, ask of this audience is we were hyper-focused on Cantor space, Baire space, and the reals. What can we say about the generic Muchnik degrees in general? And I don't think that's really been followed up on at all. They're a big structure. There's class many generic Muchnik degrees. I'm going to ask some silly questions now, and I'll explain at the end why I'm asking these particular silly questions. Are there the many? Is there a definable injection from all sets to generic Muchnik degrees? Like I said, kind of silly. Is there an anti-chain of size V? There is a chain of size org. Just take the infinite cardinals, or if you want to be a little more subtle, you can take the admissible ordinals. That's a chain of size org. Does every maximal chain have size org? That's a dumb question. But the reason you would think that might be true is that we do have in the Turing degrees, we say we have a countable predecessor property. Here we have a size of M predecessor property. The generic Muchnik degree of a structure has at most size of the structure many predecessors. Very easy to see, actually. You need too much choice, though, to go from that statement to this statement directly. Now, why am I asking these silly questions? Because, mostly I live in the world of the Turing degrees or the enumeration degrees. And one of the things I like telling students about the Turing degrees is that they're fatter than they are tall, right? There's a continuum size anti-chain, but chains are size omega 1. So, it's one of the first things I say when we start talking about the global structure of the Turing degrees. And so I thought, wouldn't it be nice if the generic Muchnik degrees were fatter, V wide, and ord tall? I have no reason to think this is true, but I thought, it'd be cute. And so these are the specific questions I'm asking. But in general, what can be said about the global structure, I think, is a more reasonable question. So, thank you.